Welcome in video 4 on policy values. In this video, we will look at asset shares. We will also look at policy values for policies with payments different than yearly. And we will also have a look at transformation of contracts. Let's start with the section on asset shares. The policy value, VT, that's the amount the insurer needs to have per policy in force at time T. This is calculated as the actuarial value of future benefits minus the actuarial value of future premium. So this is essentially a prospective view. We have a look at what is needed in the future, and it is calculated with a policy value base. The asset share at time T, what is this? This is the amount the insurer does have per policy in force at time T. This is a retrospective view because we look at the accumulated value of all the premiums that have been paid in the past minus the actuarial value of all the benefits that have been paid in the past. And the asset share is typically based on the calculated with the experience basis, so with observed mortality, with more observed interest rate and observed level of the expenses. And then there is a theorem that we have seen already in a special case at the beginning of this chapter that tells us under what conditions policy value and asset share are equal. If the following conditions hold, the premiums are calculated using the equivalence principle. VT, the policy value, is calculated using the premium basis, and the experience in the past followed the premium basis until time T. If these three conditions are fulfilled, then we can prove that the policy value at time T and the asset share at time T coincide, they are equal. Of course, these are very artificial conditions that often will not be satisfied in practice, or very often will not be satisfied in practice. The premium calculated using the equivalence principle, that's okay, that's the standard way of calculating premiums, but the policy value basis will often be calculated with a value, with a basis different from the premium basis, and moreover, or in particular, not in particular, moreover, the experience following the premium basis, that's a huge assumption that will often not be satisfied in practice. The experience will be different. For instance, the experience mortality will differ from the one that we assumed in our basis. Let us have a look at a corollary of this theorem, a special case. Suppose that the benefits are given by an endowment. So there is a person of age 50. If he dies in the next 20 years, or if he survives the next 20 years, then there is a benefit payment at the end of that, or at the moment at age 70 of amount S. And there are premiums paid. The premiums are paid for the whole duration of the contract for 20 years, provided the insured is alive. Suppose that there are no expenses. Under these conditions of the theorem, under the conditions of the theorem, then one has that the policy value at time 10 is equal to the asset share at time 10. The proof of this corollary is given here. We know that the policy value at time 10 is equal to actuarial value of future benefits minus actuarial value of future premiums. We know that the asset share is given by this expression. This we have derived that in example 7.1, but it is in fact essentially calculated as follows. This is the actuarial value at time 0 of all the premiums paid in the period between age 50 and age 60. This second part is the actuarial value at time 10 of all the benefits guaranteed in the time period between time 0 and time 10. And this is then premiums minus benefits paid but calculated at time 0. The asset share has to be available per insured who is surviving, so we have to accumulate this by the actuarial accumulation factor. Now, then we have now the equivalence principle. The equivalence principle tells us that the actuarial value of future benefits must be equal to the actuarial value of future premiums. Now we split the left-hand side of this equation in the benefits for the first 10 years and the benefits for the coming 10 years, the last 10 years. And we also split the premiums, the premium payment here in the premium payment for the first 10 years and the premium payment for the last 10 years. So this equivalence has to hold between left-hand side and right-hand side. Reshuffling the terms in this equation a little bit leads to the fact that indeed the policy value at time 10 is equal to the asset share at time 10. Let us now have a look at the following example 7.9. The benefits, the contract that we will consider here is a contract that we have considered before. The benefits are a deferred annuity on a person of age 50. From the age 60 on, he will receive a yearly annuity amount of 10,000, and there is a premium refund guarantee. If the insured dies in the coming 10 years, all the premiums that have been paid are paid back to the beneficiary. And the premiums are indeed paid for 10 years, so until the start of the annuity. And the premium is equal to 11,900. Suppose now at time 0, a total number of n such policies were sold. For instance, 5,000 of these policies were sold. And suppose also that we have arrived at time 5. We have arrived at time 5, so we know the insurance experience over the past 5 years. And there are 3 components: the investment returns, the mortality rates, and the expense. We assume that the investment return in the first year was 4.8% and 5.6% in the second year, and so on. We assume that the mortality rates that we experienced were as follows: Q50 plus T, so the probability that the person of age 50 plus T died, or the observed mortality frequency for a person of age 50 plus T was 0.0015 for any T. And the expenses that we observed at policy issue, there was an expense of 15% of the initial premium. At each premium payment, except at time 0, the expenses related to the premium payment were 6% of the premium. And expenses related to paying death claims were of amount 120. So this this gives us the insurance experience over the past 5 years. Taking this experience into account, the question is now calculate the asset share for this policy at times 0, 1, 2, 3, 4, and 5. Well, let us start at time 0. At time 0, the asset share is 0, of course. The contract has just started, no premiums are paid, no benefits are paid, so the assets available are 0. What is then the asset share at time 1? Let us calculate the asset share at time 1. So the total assets at time 0 are 0. The premium income at time 0 is n persons pay a premium P, and there is a cost of 15% that was made with this premium payment. So in the end, the premium payment is 0.85 multiplied by P multiplied by n, or that's 10,150 n. Now, the total assets that will be available at time 1 minus, that's the time before benefits and premiums paid at time 1, is the premium amount that we had at time 0, 10,150 n, multiplied by the experienced interest rate of 4.8%, gives us 10,601 n. That's the assets that we have at time 1 minus. At time 1, there are death claims to be paid. So there is a refund of the premium P for all the people who die, plus an expense of 120. And how many people die? The probability of dying was 0.015. That's the frequency of dyers that we observed, multiplied by n. So that gives us death claims. That gives us death claims of amount 18n. The total assets now at time 1 after benefits and before premiums is then 10,601 n. That's the amount that we had at time 1 minus 18n. That's the amount that we paid for the dyers. gives us 10,582 N. How many survivors are there at time N? Well, we started at time 0 with N people. The frequency of surviving was 1 minus 0.0015. Multiplying this by N gives 0.9985 N. That's the number of survivors at time 1 in our portfolio. The asset share at time 1 is then the available assets per survivor, or 10,582 N divided by 0.9985 N gives us 10,598. That's the asset share at time 1, which is of course independent of N, because it's the asset share is the amount per insured, per survivor. So we can now have a look at this asset share. We calculated the asset share at time 1. This was 10,598. In this table, you see the calculation of this asset share, not only in year 1, at the end of year 1, but also for the other years 2, 3, 4, 5. And it is a good exercise to make these calculations also for the other years. So to try to find also the asset share at time 2, 3, 4, and 5. Let us now go to policy values for policies with 1/empty cash flow. So far, we always assume that cash flows are payable, benefits or the premiums yearly at the end or the beginning of the year. Let us now assume that they are payable 1/empty. For simplicity, let us assume here that M is 12. So that there are, let's say, as an example, M could be 12. So then we have every month to pay. Example 7.10 is a contract with the following benefits. There is a term insurance on a person of age 50 for a duration of 10 years, where he will receive 500,000 if he dies, and the payment is performed at the end of the month of death. That's the 12 that indicates that the payment is at the end of the month of death. The gross premiums, there is a premium payment every 3 months. The 4 indicates that there are 4 premium payments per year. So there is every 3 months a premium payment, and the premium payment per month is P. The total premium payment per year is then 4P. And these premiums are paid for 5 years at most, upon survival for 5 years. The question that we have to answer then is determine the gross premium policy values, V, at times 2.75, at time 3, and at time 6.5. Notice that these 3 times are times at which a premium is paid and at which an eventual death benefit could be paid. In order to be able to calculate the gross premium policy values, we have to set a policy value basis. Well, we assume an interest of 5%. Survival model is a standard select survival model, and the expenses are as follows. In every premium that is paid, there is an expense of 10% related to that. The policy value at time 2.75 is actuarial value of future benefits minus actuarial value of future premiums. Well, the person is now, after 2.75 years, he has become 52.75 years, and the duration of the term insurance is still for 7.25 years. So the actuarial value of future benefits is a term insurance on this 52.75-year-old person with payment at the end of the month of death of amount 500,000. Minus the actuarial value of future premiums. And what is the actuarial value of future premiums? Well, this is as follows. The person is 52.75 years. For a remaining 2.25 years, he will pay a premium every 3 months, because the premium payment is only for 5 years at most. And there is a premium per 3 months of P, and there is a charge 10% of the premium is considered as a cost. So we can calculate the policy value at time 2.75 in this way. The policy value at time 3 is calculated in the same way. It's the actuarial value of future benefits minus the actuarial value of future benefits. Then the policy value at time 6.5 is also similar, except now we are at time 6.5 and the premium payment stopped at time 5. So there is only the policy value basis at the policy value at time 6.5 is just equal to the actuarial value of future benefits. As I said, there are no premiums paid anymore, so we get this policy value at time 6.5. Let us continue that example, and we want now to set up a recursive scheme for calculating the policy values. We start with the policy value at time 3. We have just calculated that on the previous slide. Let us now determine the policy value 1 month earlier. So that means at time 35/12, and still 1 month earlier at time 34/12, and another month, 1 month earlier at time 33/12. And we will calculate that in a recursive way. Again, we have the policy value basis, which is the same as before. And let us start with the policy value at time 35/12 as a function of the policy value 1 month later. Well, this recursion will be based on the same equation that has to hold. The available seen from time 35/12, the available assets in 1 month at time 3 minus must be equal to the required assets at time 3 minus, or more complete, the expected required assets in 1 month. Notice that time 35/12 is not a premium date. So we start at time 35/12 with the policy value V 35/12. And this is accumulated by 5% interest over the coming month. So this will be what is available at time 3 minus. What is the expected value of the required assets? Well, the probability that a person of 50 plus 35/12 dies in the next month, then we have to pay 500,000, plus the probability that this person survives the next month, then we have to set aside V3. So this is the recursion for the policy value at time 35/12, expressed as a function of the policy value at time 3. Then we can calculate the policy value 1 month earlier at time 34/12, this policy value as a function of the policy value 1 month later. This is again calculated in the same way as before. Time 34/12 is also not a premium date, and we have to have the equality between the available assets at time 35/12 minus and the expected required assets at that time. This gives rise to this expression. Let us then go again 1 month, come 1 month earlier, time 33/12. Important now, this is a premium date. Remember, the premiums were paid every 3 months. So we start with the policy value at time 33/12, and we add the premium of amount 460, but corrected for the 10% charge. This is the amount that we will have available at time 33/12 after the premium has been paid. This accumulates by interest 5, and this will be the available assets 1 month. Must be equal to the expected required assets. If the insured dies, there is a payment of 500,000. However, if he survives, we have to set aside the policy value. And this gives us the recursion for the policy value at time 33/12 as a function of the policy value 1 month later. Let us have a look at valuation between premiums dates. Another example is example 7.11. Read that example in the book. And then there is example 7.12. So we have again the same contract with the term insurance for a duration of 10 years on a person of age 50 with a payment of 500,000 at the end of the month that he dies, and the premiums are paid 3 monthly, and each 3 months there is a premium paid. The policy value basis is also the same as the one that we have assumed before, and now we want to calculate the policy value V at time 2.8. Time 2.8 is a special time as it is not time 2, it is between time 2 plus 9 over 12 and between time 10 over 12. It is between these two values. So we are, if you look at the timeline, time 2.8 is here. There was a premium payment at time 2.9 over 12, and there will be the next premium payment at time 3. An eventual debt benefit was to be paid at time 2.9 over 12. The next eventual debt benefit is paid at time 2 plus 10 over 12, but at time 2.8, there is no debt benefit. So we are at the time 2.8, where there is no debt benefit paid, and where there is also not a premium payment. Let us now denote the debt benefit of amount 500,000. For simplicity, let's denote it by S. In order to calculate the policy value at time 2.8, we first calculate the actuarial value at time 2.8 of the future benefits, and then the actuarial value at time 2.8 of the future premiums less expenses. Let's start with the future benefits. We are at time 2.8. In order to be able to express it with the formula, with the notations that we have seen, we have to split now our future debt benefits payments in the time until time, the time between time 2.8 and time 2.10 over 12, or that's 2.833. So we will calculate the actuarial value of the benefits paid in that period, plus then the actuarial value of the benefits in the remaining part. Let us have a look at the first between time 2.8 and 2.10 over 12. The actuarial value is the probability that a person of age 52.8 dies in the next 0.033 years, discounted over this period, and the benefit payment is S. So that is the actuarial value of the benefit payments or in this period between time 2.8 sorry, and 2 plus 10 over 12. And then there is the actuarial value of the rest, but calculated at time 2.8. It's an amount of S. It's a deferred now term insurance on a person of 52.8 years for a remaining 7.167 years. So from the remaining part is from here to here. That's 7.167 years. And if we calculate this, so this amount here, S multiplied by the deferred term insurance, is the actuarial value at time 2.8 of the future benefit payments from time 2 plus 10 over 12 on, and the sum of all the actuarial values in the first period and in the second period gives us this amount of 6,614. We do something similar for the expected present value at time 2.8 of the future premiums less expenses. Okay. We are at time 2.8. The first premium starts at time 3. So at time 2.8, the actuarial value of future premiums minus related expenses can be expressed with a deferred annuity on a person of age 50.2 years. It's deferred by 0.2 years. Because it only starts at time 3, and then from time 3 there are only premiums for the next 2 years, so for a duration of 2 years. This annuity amount multiplied by 0.9 multiplied by 4p gives us the actual value of future premiums less expenses, and that amounts to 3,138. The policy value at time 2.8 is then the difference between expected present value of future benefits and expected present value of future premiums, and this gives us an amount of 3,476. This example, let us have a look at the evolution of the policy value over time in this example 7.5. So in the following figure, the gross premium policy values VT at all durations are shown for the policy that we have just considered in example 7.5. Remember that there were only premium payments until time 5, and also notice that after each premium payment, the function VT jumps upwards by an amount of 0.9p. Because VT, that's the policy value at time t before premium payment, then there is an additional amount added of the premium minus the expenses, so 0.09 0.9 times the premium, and this gives us VT plus a jump upward. So we see at every premium payment, so every 3 months, there is a jump upwards of the policy value, and that's how it evolves until time 5. From time 5 on, there are no premium payments anymore, and from that time, in a smooth way, the policy value decreases until reaching level 0 at time 10, because if the insured survives until time 10, there is no benefit payment at all. Let us now look at the following contract. So we have a contract that pays this cash flow as benefit. Let us assume that M is 1 month, M is 1/12, so there is monthly payment. At the end of the month that the insured dies, he receives an amount S, but this amount depends on the end of the month in which he dies. So there is a variable benefit payable in case of death, and that benefit is paid at the end of the month of death. There are also monthly premiums paid, and the premiums that are paid are also variable. There is a premium payment PK over M at time K over M, and this premium payment continues until the beginning of the month of death. Or at the beginning of the month of death, the last premium is paid. There are also expenses related to the premium payments. At any time K over M that there is paid the premium, there is an expense EK over M. So this is a quite general contract because benefits, gross premiums, and expenses are variable. Let us now suppose that T is a premium date. We are at the premium date T. So we are at time 0 or 1/12, 2/12, and so on. And now we want to calculate the policy value at time T plus S, so VT plus S, with S between 0 and 1/M. So what does that mean? What does that mean? T plus S is a time between two premium payment dates. T was a premium date. The next premium date is T plus 1/M, but we want to calculate the policy value at a time in between. So at time T plus. We will use linear interpolation to approximate this policy value. So we will say VT plus S will be a linear combination of the policy value VT and the policy value VT plus 1/M. How do we find this formula? This is expressed in the next graph. We have to be a little bit careful. So here we have the policy value at time T, VT, and then just after time T, there is a jump upwards to level VT plus PT minus ET. So here we are at the level, we are at time T plus after the premium has been paid and the expense related to the premium has been paid. And here we have at time T plus 1/M. This is the policy value VT plus 1/M. And just after that time, there is again a jump upward. And now the question is, we want to calculate, or by linear interpolation, we want to approximate the policy value at time VT plus S. So between time T and T plus 1/M, between two premium payment dates. So VT plus S is AS plus B, for S going between 0 and 1/M, and we have to determine A and B. Well, at time S is 0, the right-hand side of this equation is B. Be careful now, at time S is 0, we do not have to take here VT, because at time S is 0, we start here, we have to go to the level VT plus PT minus ET to do the linear interpolation between this value and this. So at time S is 0, we have VT plus PT minus ET is B. At time S is 1/M, the right-hand side is A times, the right-hand side of this equation is A times 1/M plus B, has to be equal to VT plus 1/M. Solving for A and B, we find the formula on the previous slide. So this formula here. It's just important to notice this because the mistake that is often, or that could be made, is that we linearly interpolate between this point and this point. That's not correct. We have to take into account that there is a jump at time T, so we have to linearly interpolate between this point, policy value at time T plus, and this point. Now, let us have a look at policy values with continuous cash flows. So far, we always considered policy values of policies with yearly or monthly payments. So let us again first start to fix our IDs. Let's start with the discrete case. Let us assume that we consider a general contract with payment at the end of the year of that. At the end of the year of that, there is a payment SKX plus 1. So a payment which depends on the year in which you will die. And there is also a related expense EKX plus 1. That's it. You also pay gross premiums and related expenses. And the premium that you pay at time t is PT. The expense that is charged at time t is PT. And you pay these premiums starting at time 0, then at time 1, and the last payment and related expense is made at the beginning of the year that you die. Let us assume now that the policy value basis, or let us assume that we have arrived at time t and that the policy value basis is expressed by these three assumptions. The probabilities for any s larger than or equal to t are qx plus s. The interest rates in year ss plus 1 is is, and the expenses are es and es. Then from 7.8 we can find the following recursion. We can find that vt plus 1 minus vt is equal to the right hand side. So the increase of the policy value between time t and t plus 1 is equal to the right hand side, and the right hand side decomposes this increase of the policy value in three parts. First of all, the policy value increases during the year tt plus 1 because there is an interest earned on the policy value. Second part, at time t, there is a premium payment and it costs an expense et. So the policy value also increases by pt minus et, but because this is paid in the beginning of the year, accumulated by interest. So that's the premium part. And then there is a third part, minus dt plus 1 qx plus t, where dt plus 1 was the sum at risk. Remember, sum at risk, dt plus 1 is what will be paid to the dyers minus what will be paid to the survivors, or what is needed for the survivors. dt plus 1 is st plus 1 plus dt plus 1 minus vt plus 1. So minus dt plus 1 qx plus t. What is this? This is the expected death benefit, or to be more correct, the expected extra death benefit in addition to the policy value that is paid to the persons who die. So we can say this recursion tells us that the increase of the policy value from time t to time t plus 1 is caused by three factors: interest on the policy value, premiums minus expenses charged in that year, and interest plus premiums minus then expected extra death benefit payment for all the people. This is the discrete case. Let us now have a look at the continuous case. That's called, in the continuous case, the recursion will become a differential equation, which is called Thiele's differential equation, named after the Danish actuary Thorvald Thiele. Consider a general contract in the continuous case with a death benefit as t plus x and a related expense et plus x paid at the moment of death. So the death benefit is paid immediately after death, and the death benefit also depends, is a function of the moment of your death. Then there are also gross premiums and related expenses paid, but in a continuous way. So around time t, there is a premium payment pt dt. So in the interval tt plus dt, let's say there is a premium payment pt dt, and there are related expenses et dt. So premiums minus related expenses paid around time t are of amount pt minus et dt. And this is not only for time t or for the time around time t, this continuous payment stream goes between time 0 and time tx, the moment that the insured dies. So this is a notation for a continuous premium minus expense stream of, this is a notation for a continuous stream of payments of premiums minus expenses between time 0 and the moment of death. And then we have to assume a policy value basis. The policy value basis for all s larger than t, there is a force of mortality mu x plus s. For any s larger than t, there is an interest intensity delta s, and there is expense functions es and es. We assume that all these functions s, es, ps, es, u x plus s, delta s are all continuous functions of s. And then Tiller's differential equation tells us that d dt vt is given by the right hand side. How are we going to interpret this now? Well, if you look at dvt is in fact the change of vt and the change in the policy value between time t and t plus dt, or it is v t plus dt minus vt. So how is this changing in a continuous way? ddt vt is caused by three parts, as we have seen also in the discrete case. There is an interest part, there is a premium part, and there is a part related to the expected extra debt benefit payment. So the interest part is delta t vt. You earn an interest delta t vt in this infinitesimal interval between t and t plus dt. In that same infinitesimal interval, there is a premium payment pt minus et dt, and then there is also minus the expected debt benefit payment. The dt here is the amount at risk, dt is st plus et minus vt. This is the extra amount that we need for all the people who are going to die. Because if we forget the right hand, the expression with the dt, this term with the dt, this is a policy value vt that will be available for everybody, but for the ones, for everybody surviving or not, but it's for the persons who die, we do not need vt plus dt at time t plus dt, but we have to pay them the st plus et. So that's in fact here the cost of this extra payment, let's say, to the persons who are going to. That's Tiller's differential equation. Tiller's differential equation can be solved numerically. Read that in the book how this can be done. Then let us have a look at policy alterations. What is a policy alteration? Well, we have set a policy, as we know now, life insurance contracts are contracts that are set usually for a very long time period, and all the conditions, what you will pay and what you will receive, are set at time 0. Maybe the payments are only due in 50 or 60 years from now. So it might happen that a policyholder wants to change the terms of his policies. He wants to stop the policy, or he wants to stop paying premiums, or he wants to increase his benefits, whatever. We will see now how an insurer will be able to satisfy that request of the policyholder and how that is done. So a policyholder may request a change in the terms of his policy. For instance, he may want to cancel his policy. That means he wants to stop premiums and doesn't want benefits to be paid anymore in the future. In that case, we say that the policy is lapsed or surrendered. Now, a remark: if we have a policy with a substantive investment objective, in addition to protection against debt, at least part of the funds should be considered to be the policyholders under the stewardship of the insurer. So, for instance, if we have an endowment contract where there is not only a death benefit, but also if you survive, there is a survival benefit, let's say of amount 500,000. Well, if the policyholder at a certain moment wants to stop the policy, in some sense, in the past, premiums have been paid to fund that investment objective of 500,000 upon survival. An insurer cannot so just say, okay, you stop the contract, all the policy value, all what I have saved, all the extra premiums that we used to set up this 500,000 when you survive until the end, this is all lost. So the insurer cannot say that. So part of these funds should belong in fact to the policyholders. That doesn't mean that they are given to the policyholders. They are in the hands of the insurer, but they do not belong to the insurer, but to the policyholder. Therefore, it may be appropriate or a legal obligation for the insurer to attribute a lump sum called the cash value or the surrender value to the policyholder if he wants to cancel his policy. So if you have an endowment contract, or if you have a pure endowment contract, and you decide in the middle of the term of the contract to stop the contract, you have the right maybe to some amount of money, which we call the cash value. How are we going to calculate this? That's what we consider in this section 7.5. This was about canceling the policy. The policyholder may also want to stop paying premiums, but continue the policy on a reduced basis. What does that mean? I was, for instance, paying premiums for a pension that starts at my retirement age. After a while I'm still paying premiums, I don't want to pay premiums anymore. But I want that the annuity, the pension, is paid to me, still paid to me. The insurer will allow you to do that, but of course, if you do not pay premiums anymore, the amount of the annuity will be reduced. In that case, the policy is said to be paid up, and the reduced sum insured is called the paid up sum, or the paid up sum insured. Other policy alterations are a whole life insurance policy, so a lifelong insurance policy may be converted to a paid term insurance policy for the original, to a paid up term insurance policy for the original sum insured. So you had a whole life insurance contract. At a certain moment, you don't want to pay premiums anymore. And then we say, okay, we will transform your whole life insurance in a term insurance for a reduced term. Or some term insurance policies carry an option to convert the whole life to a whole life policy at certain times. You have underwritten a term insurance for a duration of 20 years, but at a certain moment you want to make it lifelong. That will be possible, of course, with a reduced amount insured. Other possible alterations are reducing the premiums, increasing the premiums, changing the amount of the benefit, converting the whole life insurance to an endowment insurance, instead of only having a payment that you want also, for instance, in accordance with the payment payment if at pension age, let's say, you can convert a non-participating policy to a profit policy, and so on. So how are we going to consider these issues? How are we going to tackle that in an actuarial way? Therefore, we have to introduce the surrender value or the cash surrender value of a policy. Let CVT be the cash surrender value at time t. CVT is so the amount on which you have the right to receive, or an amount that is attributed to the policyholder in case he wants to stop his policy at time t. CVT could be pre-specified in the contract. For instance, it could be a percentage of the sum insured, or CVT could be based on the asset share or on the policy value. So CVT could be paid on the asset share, what is available for your contract, or the policy value, what was still required for your policy at time t. In case the policy is surrendered, setting CVT equal to asset share or policy value may be overgenerous for several reasons. Alteration of a contract involves expenses, of course, so you will have to pay something for the expense related to transforming your contract or stopping your contract. Further, if the contract is surrendered, the insurer may have to realize assets. There is an amount of money available for you. The insurer can only give it to you by selling some of his assets, and this causes eventually liquidity. There is another concern, that's adverse selection. In order to avoid adverse selection, or another term, selection against the insurer, the cash surrender value may not be paid out, but used as a single premium for an altered contract for the policyholder. Or it may only be partially paid out and partially used as a single premium for an altered contract for the policyholder. What does that mean? Take as an example a pure endowment contract. A pure endowment contract, the person who has a pure endowment will receive at the moment that he retires an amount of 500,000. Suppose now this person is 10 years before his retirement age, and he realizes that he will die in the coming years. He will never reach the pension age 60, let's say, anymore. So what will he do? He will go to the insurer, he say, I will, and tell the insurer, I want to surrender my policy, give me my policy value, or give me my cash surrender value. Of course, the insurer cannot do that, because if the insurer does that, the actuarial technique is broken. If you have a pure endowment, the idea is that everybody pays the premiums as long as he is alive, but only the survivors in the group receive the survival payment at retirement. If everybody who realizes that he will not reach at a certain moment, that he will not reach the pension age, withdraws his money from his received cash surrender value, then we have a problem. The actuarial technique is broken. On the other hand, this cash surrender value is something that belongs to the policyholder in some sense. So what to do with it? Well, that is explained here. If we want to avoid anti-selection or adverse selection, the amount that the person who wants to stop his pure endowment before retirement, the amount that he should receive, or that is his own money, is not paid to him, but used as a single premium for a new contract. We will illustrate this in some examples. Policy alterations other than surrender at time t. If so we are at time t, we want to change our policy. What happens then? Well, the existing contract with given future gross premiums, future benefits and expenses will be transformed in a new contract with new future gross premiums, new benefits and expenses. What do we do then with the cash surrender value? The cash surrender value is then not paid to the policyholder, but is considered as an extra premium for the altered contract. The equivalence relation that has to hold then at initiation of the altered contract is as follows. So in the altered contract, we have the actuarial value at time t of future benefits and expenses of the altered contract, the expected present value at time t of future benefits and expenses of the altered contract. This must be equal to the actuarial value of the premiums that will be paid according to the new contract, plus the cash surrender value. So the cash surrender value indeed is considered as an initial premium in the new altered contract. Let us illustrate this by some examples. So we consider the contract that we have considered before in example 7.4 of the deferred annuity on a person of age 50 with an annuity amount of 10,000 paid yearly from time 60, from age 60 on. There is the premium refund guarantee, and there are the gross premiums paid with a premium 11,900. The basis used for the policy value and the policy alterations is the one that we used before. Interest 5%, survival model, standard select survival model. The expenses are 10% of the initial premium and 5% of all the remaining premiums. There is an expense of 100 if the death benefit is paid out, and there is an expense of 25 each time an annuity amount is paid out. Suppose now that we have arrived at time 5 and that the insurance experience over the past 5 years was as what we have seen in example 7.9. Let us now suppose that the insurer, that the policyholder wants to surrender the policy. So the policy is surrendered at time 5, and let us calculate the cash surrender value, assuming that the insurer uses this calculation for the surrender value. So the cash surrender value is based on the asset share. It's 90% of the asset share minus an extra cost of 200. Or second possibility, calculate the cash surrender value if the insurer bases the cash surrender value on the policy value at time 5. So the cash surrender value here is 90% of the policy value minus an extra cost of 200. Well, in the previous exercises, we have calculated the asset share and the policy value at time 5. So the cash surrender value based on the asset share gives an amount of 56,958. And the cash surrender value based on the policy value gives an amount of 58,723. Let us now have a second example where we, in this second kind of transforming the contract in example 7.14, we transform the policy in a paid-up policy. So suppose at time 5 the contract is altered as follows. The altered future premium level is 0. So we are at time 5 and the policyholder doesn't want to pay any premium. Of course, then the future benefits will also be changed. And the future benefits will be as follows. First of all, if the insured dies before age 60, he wants still the premium refund guarantee. So he wants to receive back all the premiums that he has paid so far, 5p. There are no extra premiums paid in the future. So it's a term insurance on a person of age 55 for a duration of 5 years with payment 5 times p, so the past premium payment. He also wants, the insured still wants this pension to start at age 60. So that's a deferred annuity on a person of age 55 with a deferral period of 5 years. But of course, because there are no premiums paid anymore, the same amount of 10,000 cannot be paid anymore yearly. So the amount that will be paid is X. And we want to determine this reduced annuity X in case the cash surrender value is given by 56,958. Well, in order to find that, we use the following equivalence relation. The actuarial value of future premiums in the new contract, but that's 0, there are no premiums paid anymore, plus the cash surrender value, which is considered as an initial premium, has to be equal to the actuarial value now from all the future benefits. And the actuarial value of all future benefits is the cost of the actuarial value of the premium refund guarantee plus the actuarial value plus related expense of the deferred annuity. And we can solve this for X and find that X is 4,859. So if at time 5 we want to stop paying the premiums, but we still want the annuity contract, the original annuity payment of 10,000 per year reduces to a payment of 4,859 per year. Let us now have a look at another way of transforming the contract at time 5. We transform now the deferred annuity in a pure endowment. So suppose that we have arrived at time 5 and we still want to continue the same premiums. So we pay the remaining 5 premiums according to this temporary annuity, and the premium level remains the same, 11,900. But we want to change our benefits as follows. First of all, the premium refund guarantee remains the same, but instead of receiving an annuity amount of 10,000 per year from the age 60 on, no, what we want now is if we reach the age 60, we want an amount of S. Question is then, and well, some remark, in case the S is paid, the insurer has to charge an expense of 100, or in his calculations will charge an expense of 100, and we want to determine now S. What is then the amount of the pure endowment? And we assume that the cash surrender value is 56,950. Well, again, we work with the equivalence relation. The cash surrender value is considered as an initial premium plus the actuarial value of all future premiums minus related expenses must be equal to the actuarial value of all future benefits. And the actuarial value of all future benefits is the actuarial value of the premium refund guarantee plus the actuarial value of the pure endowment. And this is an equation with unknown S, and we can then solve this equation for S. Then, concerning policy alterations, there is another example in the book 7.15. Please have a look at it there. Section 7.6 is about retrospective policy values. So far, we always looked at prospective policy value. We defined the policy value as what is needed in the future minus what will be paid, or what are the benefits paid in the future minus what are the premiums paid. We can also define policy values in a retrospective way, in the sense of what is the accumulated value of all the past premiums minus the actuarial value of all past benefits. This is related to the asset share, but the asset share is in fact a retrospective policy value with a special basis, namely with the experience. So everything about the retrospective policy value, please read it in the book. Then there is also some remarks about, or a section about, negative policy values. So far, we always assumed, or we always found, that our policy values were positive. That means that the insurer has a positive liability towards the client. What to do in case of negative policy values? Read this also in the book. Then there is also a section on deferred acquisition expenses and modified premium reserves. If the acquisition expenses are not all paid at time zero, but eventually later, how can you tackle that kind of problem? Please also read that in the book. And then we have just seen policy values, and policy values are a kind of reserve that the policyholder has to cite. We will, in section 7.9, consider more general setting of reserves in an insurance context and what is the place of policy values in that general setting. Read this also in the book. And then there is notes and further reading. Also, I invite you to read that in the book. So this is the end of this fourth video on policy values. Thank you for your attention.